Hello and welcome to this webinar titled Introduction to Magnetic Simulation using EMS for Inventor. My name is Arvind Krishnan and I'm the Director of Product Management here at EMWorks, and I will be your presenter today. On behalf of EMWorks, I would like to thank you all for attending this webinar. Before we start, let me just convey to you a few bookkeeping items. We are going to use the Demio platform for this webinar, and as attendees, you will have access to the chat section. It's on the right side as you see here. Now, if you have a question, I request you to kindly type in the chat window, and towards the end of this webinar, we will make an effort and answer each one of your questions. Sometimes during the webinar, my colleagues will be able to answer to your questions directly via the chat window. Now let us take a look at the applications that we will be covering in this technical portion of the webinar. We will actually talk about two applications in this webinar pertaining to the magnetic solvers in EMS for Inventor. As a first application, we will consider a solenoid actuator under DC current. And in the second application, we will consider a complex busbar arrangement, and we will see the forces acting on each of those busbars due to short circuit current. Also, we will compute the temperature distribution in the busbar during normal operation. Let us now proceed with the technical portion of this webinar. Hi, in this example, we will see how EMS for Inventor can be used to simulate a DC actuator working under a DC current. What are the objectives of this simulation? First, we would like to find out the force acting on the plunger and how this force varies with the gap between the plunger and the core. Now let us get back to EMS for Inventor. In this particular model, you see the entire DC actuator. This actuator was created using EMS for Inventor. Let me take the front view so that we can understand the various components of the actuator. We have the plunger here that I am highlighting in green. Next we have the core, and finally we have the coil. Now the coil is excited using DC current. When it is excited using DC current, there is a magnetic flux that is circulated in the outer core and through the plunger. As a result, the plunger tends to close the gap that exists between the plunger and the core. Now this is going to manifest as a force acting on the plunger, and EMS for Inventor will be able to capture this force. That is one of the objectives. And you see that the gap between the plunger and the core can be altered using a dimension parameter in EMS for Inventor, and we will vary this dimension and study how the force varies for various gap values. Now to start a simulation in EMS for Inventor, we go to the EMS Feature Manager tab. In EMS Feature Manager tab, the simulations are organized as studies. To create a study, we right-click and then select Study. For the magnetic simulation, we have three different study types: magnetostatic, AC magnetic, and transient magnetic. In this particular simulation, we will be looking at the magnetostatic solver type. Once the study has been defined, we now assign materials for the various components. The coil is made of copper. The plunger and the stator is made of steel, and then there is also air geometry surrounding all these solids. To apply material, you have to right click on the part and select apply material. EMS for Inventor has a material library that comes standard with the product, where you can select some of the predefined materials, or you can actually create your own material and use that for simulation. Once the material has been assigned, we assign what is called as a coil. This is the place where we tell the program how much current is flowing through the coil. Here we select the components that comprise the coil. We also select the cross-section face. So let me go ahead and make a turn of this model so it is very clear that the cross-section face that we selected is indeed the face through which the current actually goes. Now coming to the value of the current, we have 328 turns of copper with 19 gauge copper, and each turn carries a current of 1 ampere. So the total amp turns in this situation is 328 amp turns. Here we specify the wire gauge of the material used to wind the coil and so on. Once the coil is defined, the last step is really to request the program to compute the force acting on the moving plunger. Now we would like to study this model as a parametric simulation where the gap length between the plunger and the core will be varied. So to do that, we actually enable what is called as design scenarios. Now we have created a variable called gap length in Inventor, which can be used to vary the distance between the plunger and the core. Now we would like to study this model for 4 different gap lengths, namely 0.5 millimeters, 1 millimeters, 1.5 millimeters, and 2 millimeters. Now let us take a look at the results that we get from the simulation. Now the results in the simulation are organized in 2 different locations. All the numerical value of the results are available in what we call as the result table. Here the values such as, say, the force acting on the plunger, in this case it is around minus 9.64 newtons for this scenario where we have 0.5 millimeter gap. The minus is because the positive y-axis is facing upwards and you will get a negative force acting on the plunger. In addition to the force, one can calculate the resistance of the coil. EMS also calculates the flux linkage as well as the inductance of the coil. Now I can vary the scenario here. For example, I can go to scenario 4 and similarly compute the force. Notice a marked difference in the force from minus 9.6 all the way to minus 1.8 newtons. Why? Because in scenario 4, the gap length is 2 millimeters compared to half a millimeter that we had in scenario 1. We can also study what we call as qualitative results. In this particular plot, we will study the magnetic flux density as a section plot through the DC actuator. Notice regions of high magnetic flux density shown in red and regions of relatively lower magnetic flux density shown in green and blue respectively. Now this allows you to study how much flux density is there in different parts of your model. It also allows you to understand when the steel gets saturated due to the applied current in the coil. So in this example, we see that the maximum flux density is close to 0.95 Tesla, and that is there in the steel plunger. Now this is for a gap length of 0.5 millimeter. Now we can right click and then edit this plot, and then we can change the scenario. So for example, let us go to scenario 4 where the gap is much higher, 2 millimeters, and when we say OK, the plot updates and you are now going to see the new magnetic flux density plot where now the gap length is 2 millimeters. You can again see the relative areas of high magnetic flux density, but the maximum value of the magnetic flux density has reduced to 0.86 Tesla. So this is a qualitative way of understanding what happens in our model with respect to the magnetic flux density. Here is a plot of how the force changes with the gap length. As you can see, as the gap length increases, the magnitude of the force reduces rapidly from almost close to 10 newtons when the gap length is 0.5 millimeter to less than 2 newtons when the gap length is 2 millimeters. In the next model, we move on to the AC magnetic solver. Using this solver, we will simulate a busbar arrangement as shown here. What will be the objectives of this simulation? First of all, we would like to simulate this arrangement of busbar under normal operating conditions, and we would like to see the temperature distribution in the busbars. And finally, we would like to simulate a case where we have a short circuit, very high current through these bars. These high short circuit currents produces large Lorentz forces on the bars, and the objective of the simulation will be to calculate the forces acting on each of these bars. Let us take a look at the busbar model that we are going to simulate. Now it has plates or busbars made of copper, and it has 6 such bars that carries current, and there is also 2 such bars that does not carry any current. So these busbar arrangements carry 3-phase current. We create a study to take care of the normal conditions. First, the study that we create is called as an AC magnetic study. In the earlier simulation, we saw the magnetostatic study. Now the bars are all made of copper, so you see here that all these bus bars are made of copper, and these holding bars, they're all made of some kind of insulating material. Okay. These holding bars are actually designed to keep the bus bars in place. Now, during the normal operating condition, there is going to be an I squared R heat loss in each of these bus bars. Now, to evacuate this heat, we apply what is called as a convection boundary condition. Now, in this convection boundary condition, all the outside surfaces of the bus bars, as well as these holding bars, are convecting to the surrounding air using natural convection. Now let us take a look at the definition of the current through each of these bars. Now the first 2 sets of bars actually don't carry any current, so we have applied a 0 amp RMS value. The next 2 sets of bus bars, they actually carry 5000 amperes of current. Okay, and the phase angle is 0 degrees. Because it is 3-phase, then the other 2 bars carry 5000 amperes but a phase angle of 120 degrees. And finally, the last set of conductors, they carry Again 5000 amperes at 240-degree phase shift. Thus we make sure that these bus bars carry three-phase current. And this is the normal operating condition. The main reason that we are doing this simulation is really to study the temperature distribution in these bus bars. Okay, so let us take a look at this result. So namely 3D temperature distribution result. Now here is the distribution of temperature in the bus bars. Notice the high temperature value of 182 Fahrenheit in the extreme bars, and also as you move inwards the temperature reduces. And you can also see how hot these holding insulators get because they are in contact with these bus bars. Now getting to know the normal operating temperatures when these bus bars are carrying 5000 amps of current is important, because that helps you to understand how hot these areas get, and it also helps you to appropriately design any kind of cooling system you might need to incorporate to cool these bus bars. Now as a second simulation, what we are going to do is we are going to study the forces acting on each of these bars when we have a high current, something like 25,000 amperes passing through each of these bus bars. To do that, we've actually created a similar AC magnetic study. And we have applied the material, same, we have applied copper to all of the bars. And now, if you look at the current through each of these bars, you see that it carries 25,000 amperes of AC current. And the next set of bars also carry 25,000 amperes, but at 120 degrees phase shift, and finally 25,000 amperes at 240-degree phase shift. If you look at the study properties, you will know what is the frequency of the current carried by these bus bars, and that happens to be 50 Hertz. We did the thermal simulation in the previous study, so we are not going to include thermal here. Now, we would like to understand the Lorentz force acting on each of these bars. So, I've selected each of the bar and I've requested the program to compute and give us the value of the Lorentz force. So, you can see the force has been requested now for the second bar, and so on and so forth. Now, once we have run the simulation, we will go ahead and take a look at the results. Now the results are organized in the result table. We can take a look at the Lorentz force. When I come to the force tab, you can see the Lorentz force. So Lorentz force 1 corresponds to the extreme bar that I'm highlighting right now. And you can see that the force actually has two major components, force in the x-axis and force in the z-axis. So let me take the top view so that it's very clear what the x-axis is and what the z-axis is. Similarly, for the second bar, the Lorentz forces are very high. It's close to minus 362 newtons along the x direction, and 362 newtons along the z direction. So you can really see the magnitude and the direction of the Lorentz force in each of these bars, and you can also kind of calculate if these forces are large enough and if you have supports that will withstand these forces. So it's very useful for designers of these busbar systems to study these systems under very high current. Although these currents might occur only for a small fraction of time, nevertheless during a short circuit, very high currents go through these bus bars, and as a result a very large amount of Lorentz force is created, and EMS helps you to study the magnitude and the direction of these forces. In addition to it, as a recap, under normal operating conditions, we were able to understand the temperature distribution in these bus bars, and when you have abnormal operating conditions like very high currents such as 25,000 amperes going through these bus bars, we can study the Lorentz forces acting on each of the bars. And finally, here is a plot of the current density. So it also gives you an idea of how much current is going through each of these bars. And you can see that almost 4.6 into 10 to the 7 amps per meter square is really the maximum current density carried by these bars. Also, you can see the distribution of the current. They tend to cling to the outer surfaces of the bar, and also due to the eddy effects, you can see how the currents are distributed in the inner bars and so on. So EMS not only allows you to look at the forces as well as the temperature distribution, but it also allows you to understand the current density distribution through your bus bars. Now let us come to the concluding part of this webinar. Let me recap what you saw today. We looked at 2 of the 3 solvers that comes with the magnetic simulation in EMS for Inventor. We looked at magnetostatic and AC magnetic solver. And the third solver, which will be a topic for a future webinar, will be the transient magnetic solver. Using the magnetostatic solver, we solved a DC actuator to find the value of the forces acting on the plunger based on the gap between the plunger and the core. We also used what is called as a parametric simulation, where a dimension in Inventor can be used as a parameter, and you can study the behavior of the model as you vary the parameter. Using the AC magnetic solver, we solved the busbar problem. We coupled the busbar simulation to a thermal simulation so that we can compute the normal temperature distribution when the busbar is carrying its rated current. We saw how EMS can be used to compute forces. We used the second simulation to compute the Lorentz force acting on each of those bus bars. And we also saw how EMS can be used to visualize field results such as magnetic flux density, current density, etc. So, if you are looking to solve magnetic problems and you use Inventor as your primary CAD, then look no further than EMS for Inventor, which can help you solve a lot of practical problems right inside Inventor. Thank you for watching this webinar. On behalf of EMWorks, I would like to thank you all. And if you have any questions, please use the chat window, and we will conclude this webinar by answering some of your questions. Thank you again, and see you in a future webinar.